So one of the key questions that has been posed by the decadal survey is how does stellar activity affect evolution and habitability of extrasolar planets? And ACCESS is extremely well positioned in being able to answer some of these questions. This chart shows all of the different components that go into a characterization of extrasolar planets. And one full quadrant of this chart it has to do with the properties of the star around which this planet is orbiting around, because without understanding the stars, we can't really understand the planets to begin with. And many of these properties that are highlighted are highly correlated with X-ray emission. For example, X-rays are very good indicators of age, activity, variability, and others. And it is extremely important for us to be able to characterize magnetic activity of the host stars, because if the activity is high, there is a high probability that the flares from the star could actually strip the atmosphere of the exoplanet, which would severely put a damper on its habitability. The reason why it is a concern is because the most common star that we have in the universe are the M dwarfs. They are about 10 times as abundant as solar type stars. So M dwarfs have a lot more planets than solar type stars do. But because M dwarfs are significantly less luminous, their habitable zone is significantly closer to their star. Plus, the M stars themselves tend to be fairly active. These planets would receive 400 times as much X-ray irradiance in their habitable zone than we do here in our solar system. So the possibility of these planets having their atmosphere stripped by flares would actually be relatively high. But when we look at the X-ray activity, how we can when we look at the magnetic field in general, there's a couple of ways we can track them. One of them, most directly, would be the X-ray emission. A couple of others would be through optical variability, because when you have strong magnetic fields, you also develop spots on the surface of a star, and as these spots rotate in and out of the field of view, you get this variation in flux that would occur on the timescales of the rotational period. The larger the spots, the larger the amplitude of the variability is going to be. It's not necessarily a perfect correlation, because it does depend on the inclination of the star. It does depend on some assumptions about the spot geometry. But if we don't have a more direct method of measuring the magnetic activity, such as through the X-ray emission, it will do in a pinch. And also the rotational period of a star itself is strongly correlated with its activity, because as stars evolve, the rotational periods spin down from its magnetic dragging. And right now, it is actually an extremely interesting time to analyze how stars evolve, because right now we live in the era of Gaia. Gaia has allowed us to measure many of the stellar properties much more directly than we have been able to before. And in one area where Gaia has been particularly useful is in its ability to help finding new clusters and new moving groups. For example, here, all of these yellow sources are the clusters that have been known within 1 kiloparsecs prior to Gaia. And all of these blue dots are the sources that are part of the moving groups that have been discovered since Gaia. And so you can see there's a significant difference between them in terms of the spatial coverage and the number of sources. So in total, within 3 kiloparsecs, we have been able to identify on the order of 8,000 different moving groups containing approximately 1 million sources. And the neat thing about all these populations is that the stars within them have formed at the same time, so we can use isochrone fitting in order to estimate their age. And as you can see, they tend to follow pretty nice isochrones that you have as the youngest populations having still sizable pre-main sequence component. Eventually, they drop down onto the main sequence. And then after approximately 100 million years, these stars in green on the high mass end begin to die off, so you develop a fairly clean turnout. So through isochrone fitting, we have been able to determine the ages for approximately 1 million stars, allowing us to probe evolution of these stars over time. But just by looking at the optical variability, what we find is that at the youngest ages, stars tend to be extremely variable. So they tend to have very large spot sizes. The stars that remain fully convective throughout their lives, the M dwarfs on the low mass end, tend to also have pretty high level of activity. They also have large spot sizes throughout their lives. So if we look compare back the G dwarfs and the M dwarfs, not only is the habitable zone much closer around the M dwarfs, but also their activity persists through pretty much throughout their lives. So those planets would also receive a significantly larger dose of the radiation. But as soon as a star begins to develop a radiative core, the degree of activity within that star begins to decrease. And then after it reaches the main sequence, this king right over here, it just continues to precipitously decline from there on. So again, this isn't a very direct probe of activity. There's a lot of assumptions that go into converting variability to something physically meaningful. But it's still rather neat just how well it is able to follow our theoretical models of stellar evolution. Rotational periods also are strongly correlated with the activity because, as I mentioned before, the strong magnetic fields tend to slow down the rotation of the stars. And here we're looking at the period, the dominant periods within the light curves, color-coded by the age as a function of temperature. And you see there is this gradient that the youngest stars tend to spin fairly rapidly, but then over time, they eventually slow down their rotation. And this, in principle, allows us to measure ages for even larger number of stars in the future. But all of this is, again, an indirect probe of activity. X-ray emission would be a much more direct probe. Oh, before I forgot that. So the rotation periods also can give us an angular momentum, which is a bit cleaner in terms of being able to demonstrate that these stars spin down across all temperatures. But yes, but the magnetic fields are strong, and X-ray emission are strongly correlated with the activity that we measure in the optical. This is a rather interesting plot. This is from almost 20 years ago, where we certainly didn't have as good of a sensitivity for optical variability. We didn't have as comprehensive a sample of X-ray emitting sources. But what they have found is that the stars that are periodic, that is to say, strongly variable enough to be detected 20 years ago with ground-based photometry, tend to also have highest X-ray emission. So this is let's say the stronger the variability of a star, the stronger its X-ray emission is going to be. It is possible to compare the X-ray activity to the rotation directly. There is this interesting knee that at very fast rotations, this is the rotational period, this is the Rossby number. At very fast rotations, the X-ray activity tends to flatten out because the magnetic fields of these stars are saturated. As the rotational period increases, as you've transitioned to the regime where you have slow rotation, then the X-ray luminosity tends to decrease ever so slightly as well. So there is a significant correlation between all of these different properties. That is to say, they are all tracing magnetic fields, and we can use a combination of them to act as our tracers, but it's really through combining all of the different properties where we are able to understand more about these stars. Just like rotational periods and the spot sizes tend to vary as a function of age. So does the X-ray emission itself. Very early on, these stars tend to start their lives to be very X-ray luminous, very easily stand out from the field. And back in the days prior to Gaia, X-ray luminosity was one of the best ways for us to actually identify the pre-main sequence stars, because after they lose their disk, they tend to resemble the field stars. But after a while, the X-ray activity begins, X-ray luminosity tends to decrease precipitously. The thing is, these plots are pretty sparsely populated, because unlike currently with large surveys that allow us to measure the variability of the stars across the entire sky, with X-rays, we have been limited to significantly fewer fields of view that have been observed with Chandra. And so, because of this, there's a lot of variability in this plot as a function of spectral type that we still don't necessarily have a good handle on what precisely it correlates with. We do have a slightly better handle on just the youngest end. So there has been a recent study that extends only up to around 30 million years, where they have been able to observe on the order of a dozen of young clusters with Chandra. And it's interesting to see just how much the X-ray luminosity evolves for the lower mass stars versus for the higher mass star. That is to say, the lower mass stars tend to stay X-ray bright for longer periods of time, as in the stars that are that do have radiative atmospheres. But still, there's still a lot about the X-ray activity at these, even at these ages, that we don't understand. And kind of the key issue is that the data we currently have isn't enough. The golden standard of X-ray astronomy when applied to young stars is the Chandra-Orion ultra-deep field. So many sources actually over here are from the survey. What the scoop field is, it was able to obtain a continuous 800 kilosecond exposure, which is approximately 14 days. And that is really a lot of time to spend staring at the same region of the sky. And throughout this time, they have been able to achieve the sensitivity of flux of 10 to the minus 16 ergs per second per centimeter squared. So they would have been, they are able to detect approximately 90% of all of the young stars that we know of, period, in this field of view. So it is an incredibly deep survey. Of course, there are certain limitations that it has had. For example, as you know, there's an issue with an off-axis, the PSF, and you can actually see in this image that in the center of the cluster, the pointing is pretty crisp, but the further and further you get away from it, the more and more distorted the sources become. So access will certainly be able to offer an improvement just in terms of the resolution, because when we're dealing with these clusters, they tend to be fairly dense. It is important for us to be able to resolve individual stars and to avoid the source confusion as much as possible. And it's one thing when we're actually looking at the clusters that are fairly nearby. The further and further we get, the closer and closer, the more compact the stars are going to be together. So we certainly do need to be able to resolve that. But also, there is an issue of the scale. So here is the full extent of the Orion complex. This is the entire constellation. Here we have the head, the shoulders, the belt, the sword, the knees. So you have young stars forming throughout this entire region. And it has multiple populations with ages of less than 10 million years. Orion Nebula, which is the most active region of star formation in this area, is located right over here. So the COOP was observing Orion Nebula, but it wasn't able to observe its entirety, but it was able to observe only a small part of the most active part of the Orion Nebula. So we are just probing kind of the pimple end of star formation, where we can take a look at the X-ray activity in the densest part, the part that is most subjected to the ionization from the nearby stars, but we don't necessarily have a good handle on the more diffuse part of the Orion complex or any other region for that matter. Because when we have been observing these fields, we have been primarily focusing on the clusters as opposed to the more distributed modes. And we do know that some aspects of star formation and stellar properties do depend on the environment. We don't necessarily have a good handle in what way precisely, but for example, the multiplicity of stars is affected by the environment. And it's possible that the activity is also affected by it as well. Axis will have the same field of view as Chandra approximately, but because it will have a much greater sensitivity, we would be able to observe more fields in the same amount of time, which hopefully will give us a greater variety of the populations of both different ages, different sizes, different masses, etc. Plus nowadays, since we do have so many different populations that we have been identified, we might be able to hope that we will be able to identify some of these sources with known ages serendipitously in other fields as well. Of course, Axis isn't the only survey out there that does X-ray astronomy. There's also Rosita. Rosita has the advantage of being an all-sky survey, but unfortunately it does have an extremely low sensitivity. So at the end of the mission, it will be able to achieve sensitivity of only 10 to the minus 14 centimeter squared per second. So that's about 2 orders of magnitude lower than we had for the COOP survey. So with Rosita, you can't really have much sensitivity to push beyond 100 parsecs, and even then you're primarily limited to just the youngest stars. For example, with Rosita, they have been able to get a rather nice survey of SCO-7 star forming region, which is located approximately 120 parsecs away. But again, you wouldn't be able to get all the populations with Rosita to the same degree at the same distance. And unfortunately, in our immediate solar neighborhoods, we live at a rather interesting part of it. The sun is located very close to the center of the local bubble. That is to say, we don't necessarily have much of the molecular gas within 100 parsecs. Therefore, we don't necessarily have many young populations within 100 parsecs. And even on the older populations, and there's very few of them within the immediate vicinity. So we do need to get pretty far out to be able to identify a sizable number of them. But just together, as we are observing many more of these populations with axes, we should be able to get better constraint on the X-ray luminosity of these stars. So just to summarize, axis will help us to characterize stellar activity with age in a more direct way than we have been able to in the past with optical surveys. It will help us to better characterize flaring of these stars, and will help to constrain the origins of the scatter in the X-ray age luminosity relationships. Just because we will be able to have more data than the handful of clusters that we have been previously able to observe. And of course, it will have a lot of synergy with other surveys, as we will be able to probe same physical processes from multiple ends. Thank you.
Great job, Marina. That was really good to listen to. So if people have questions, they can raise their hands. I'll ask one quick question while people are thinking. So as far as, the likely exoplanets, identified by test or direct imaging or whatever, how interesting are those in terms of looking at their X-ray activity, and what have people sort of found? I mean, because of course, the very detailed studies of hundreds of thousands is really interesting, but I'm also wondering about the ones with known exoplanets.
Yeah, certainly. I am not as familiar with exoplanets as I am with stars themselves. But certainly, I think people have tried to look at some transits with X-rays before on a handful of stars. And I think they have been able to see some of these transits actually being brighter in X-ray than they have been in optical regime. So that would be interesting, and certainly having a larger census of these stars would help. In terms of the youngest populations, just any sort of periodic signature in the X-ray emission is interesting, because even so, the X-ray emission in the stars that still have protoplanetary disks is quite rare. There have been some detections of hot spots on the surface of these stars that are X-ray bright. That is actually the result of the accretion stream from the protoplanetary disks onto the host star. So just, any sort of the periodic activity that can be attributed to either the disk or the planet would be interesting, because then we'll be able to actually build up the census of these sources.
Great. So Mark, you want to ask your question?
Oh, yeah, thanks. It was very interesting. So my question has to do with the trapezium. I'm just curious, are there any upper limits on X-ray emission from protostellar disks that may have been identified in that region, or
Yeah, so when we're talking about X-ray emission, we're primarily talking about the stars, the emission from the photosphere.
Yeah.
In the stars without disks, because the X-ray emission from the stars in disks tend to be a bit lower. The disks tend to process a lot of light, so very little of it actually gets out.
Since it was such a deep observation, I was hopeful, I guess.
No, there are some sources, and but the stars with disks have a higher hardness ratio, if I remember correctly. So if you are able to look at the very, very far X-rays, then you have a better chance of detecting these sources. I still think it's primarily emission from the photosphere itself. So I think they have a very similar origin. So it's not the disk that is producing the X-ray luminosity. It's just that the emission is coming from the photosphere and the disk is suppressing it.
Yeah, and then some absorption. Okay. Yeah, thank you very much.
Okay, Chris.
Yeah, thanks. Well, very nice talk, Marina. Thanks. Two sort of related questions. One is for that beautiful Chandra data in Orion. It gets very crowded in the middle. So at what point do we sort of hit a formal confusion limit? Are we getting there with Chandra, or will we get there with Axis?
Yeah, no, in the center, so in the center is a resolution on the order of 1 arcsecond, and that's usually is good enough. And we're actually doing some simulation for even more distant region in Carina, which is approximately 2 kiloparsecs away. And there have also been some extra observations with Chandra there, and plus there have been a variety of different other surveys that we were able to cobble together to get as complete of a catalog as possible. And generally, as long as we can get the pointing within 1 arcsecond, we wouldn't necessarily need to worry about the confusion all that much.
Okay, thanks. And then sort of the related question is, so in settings where we might have a deeply embedded young star cluster, and presumably we're then sort of staring at the harder X-ray emission, what's your thoughts on how crowded those fields would be, and again, what the typical kind of separation would be?
I mean, it always depends on the cluster size. When thinking about some of the embedded clusters, I mean, Orion Nebula is one of the most extreme cases. There are a couple of other young, mostly embedded clusters in the solar neighborhood, NGC 1333, IC 348. They are not anywhere near as dense as the Orion Nebula, but they're also all a bit closer in, so they are at 300 parsecs rather than 400 parsecs that the ONC is. So again, in general, as long as we have the PSF that is on the order of 1 arcsecond, which is what we often deal with optical surveys, that is usually good enough.
Okay, thanks.
Okay, are there any other questions in our last minute or so? If not, well, thank you, both of our speakers. Those were really great talks. And I'll look forward to seeing everybody in a month. And take care.
Yeah, and to answer the question about the, I think that's so it originates from the center, which is where we have the theta 1 RC. So it may be just a saturation from one of the stars that kind of created some data issues.
Okay, but it's a real feature in the data, if you like. It's
Well, it is in the data, but it is not physically there.
Wasn't an arrow drawn on the PowerPoint or
No,
something.
no.
Okay. Yeah, good. Thanks.
All right. See you, everybody.
Bye.